turn on. What the heck? Come on. There we go. Dropbox, DIFC, workbook, physics, materials, ideal gas law. What was the last thing we did?
Triple point.
Oh yeah, triple point. That was fun. Okay, this is where we're continuing now. You okay? What's wrong with you? Are you sure? Okay. Is that a new top? It is? Yeah. I've only seen you wear black recently, so dark blue now, that's nice. Okay. How do we count in physics? So, what I mean is, when we count, we do use a unit. So imagine we had some water. We don't say we have, we could say 10 to the 23 molecules of water, but we use a unit to count. For example, bakers count in 13s. That is, 10 baker's dozens is 130. Farmers count in 12s. 12 eggs, 24 eggs. I don't know if it's the same in your country. Is it?
Yeah.
You buy eggs by 6 or 12, yeah. Same in China? How many eggs in a carton of eggs?
The one basket.
Yeah, how many eggs? Is it 6? 12? 18? How many?
I'm not sure.
Okay. Do you guys know back home? No clue. Do you know, Kim? No? Okay, well I think it's 12. Okay. In physics we count molecules in units larger than 13 because you have so many molecules. So you might think, well, maybe we should count in millions. You have 1 million molecules, 2 million molecules. And actually that's no good because that's too small. Well, what about billions? 1 billion molecules, 2 billion molecules? No. We don't use those units because even those are too small to use in physics. So we use something that you probably heard of in chemistry called Avogadro's constant. This is a pretty big number, and this is how we count in physics. So we count in something called moles. So mole is bigger than 1 million, bigger than 1 billion, bigger than 1 trillion, very big number. A mole is a mole of something that we counted. It doesn't matter what it is. It can be molecules, cups of coffee, stars, whatever. It's 1 Avogadro. That's how much a mole is. So how much is an Avogadro? 1 Avogadros is 6 by 10 to the 23. Now, have you done that in chemistry with Lorraine? Yep, you have, okay. And does she use 6 or 6.02?
6.
Yeah, we use 6.02. So the definition you'll need, you can write that box down. Got that? Yep. Yeah. Okay, continue? No, not yet. Do you use any special letter to represent Avogadro's number in chemistry? Because here, I use Na to represent Avogadro's constant. Do you guys use any special value? No? Is there an N? You do in Lorraine's class? Do you? Yeah, but I mean Avogadro's number. Do you use any constant, any symbol for it? What is it on your, is there an Na on your calculator? Who has the Casio one? Is there an Na on it? I mean on the lid for constants. Let's have a look there, Joe. Let's see. There is. It's number 24 on this one.
Oh yeah.
Yeah. Okay. That's good. So why don't you type in that constant, see what value they have. What is it? How do you do constants again? What is it? How do you do it? Shift 7, and then we're looking at 24. There you go. See, there it is there. You have it? You don't have constants on that? Do you have it on that one? Are you sure? What happens if you press Shift and 7? What do you get? Okay, yeah, you don't have it. Right. Continuing. So, if I have 1 mole of H2O, how many molecules of H2O do I have? 6.02 times 10 to the 23. Same goes for a mole of cups of coffees or stars. You have that many. Okay. Now, imagine I have 1 mole of cups of coffee. That's a lot of coffee. What would the mass be? So let's just roughly calculate it, okay? What's the mass of 1 cup of coffee, roughly? What would we say this is? Roughly. 0.1? I think it might be a bit more than 0.1. Maybe 0.2. Maybe 0.2. Yeah. So, I want you to calculate for me what is the mass if I had a mole of this.
So times about 6.
Mm-hmm.
1.2.
Times 10 to the 23. 1.2? 23. So roughly 10 to the 23 kilograms. Yeah? That's obviously a big number. This is called the molar mass. Basically the actually, have you done molar mass in chemistry? Yeah. The molar mass is the mass if you had a mole of the material. It's actually common to use grams for this because it's usually a small number. Now, in my example of the coffee cup, it was a big number. But because molar mass is usually small, it's quite normal to use grams. Okay? But I mean, you could use kilograms, that's fine, but usually it's grams. Like, for example, I think you probably know the molar mass of carbon 12 is 12 grams? Is that right? Yeah. So, like, it's a small number. Can you write this definition down, please? The molar mass. Got that? Yeah. You've learned some molar masses in chemistry, like carbon-12 and hydrogen and maybe things like this, oxygen or something, yeah. What are you actually doing in chemistry? It is this balance and equations? What did you do in your last class? Yeah, okay. So it's related to this then. That's good. That's good timing. For example, does anyone actually know the molar mass of H2O? If you had a mole of H2O, what its mass is? Does anyone know this?
18.
It's about 18, yeah. It's not exactly 18, it's about 18 grams per mole. Okay, some important notation. So, we usually let the big N represent the number of molecules, and the small n is the number of moles. Now, is that the same as chemistry, or is that different? You never use big N. So what letter do you use for number of molecules and number of moles? What? No letter. Well, I use big N for number of molecules and small n for number of moles. Okay? It's actually important to remember. So, we have this formula. The number of molecules equals the number of moles multiply Avogadro. Now, you probably have this formula in chemistry. Maybe you just don't write it like this. How would you write it? Or you just write it in words? Words? Okay, great. Number of molecules equals number of moles times Avogadro. Is that okay? Yeah, if you're not confident with that, just write that down. Does Lorraine not like using symbols or letters in class? Is it always words?
I think she did.
Only for number of moles she uses the small n, but for number of molecules she uses number of molecules. Molar mass she uses MR.
Yeah, okay. Okay.
And mass is big M.
Okay.
M equals S.
No? No big deal. Don't mix up the two. This is how I like to remember it. Here's your little hint to remember, okay? Big N is bigger than small n. So I remember. So, big N represents molecules, because you have more molecules than you have moles. That was a nice little memory trick. Big N is bigger than small n, no? Yeah, big N is number of molecules. And small n is number of moles. Yeah? Okay, continue. Yeah? Here's one question. Now, I would hope from your chemistry class you can do this one. You'll make Lorraine very angry at you, I guess, if you can't. So let's have a look at this one. 1 litre of water is at room temperature. The molar mass of H2O is 18.01528 grams a mole. How many moles of H2O are in 1 litre of water? Now that's a little bit tricky, but you actually did a formula in chemistry with your molar mass. What did you have? You had like total mass equals molar mass multiplied by number of moles. Was something like that? Yeah. So you should actually use that, I think, if you wanted to get the first answer. How many moles? And then once you have how many moles, how do you get how many molecules? So if you know the number of moles, how do you get the number of molecules? The other one multiplied by Avogadro, yeah. And then you can tell me how many oxygens and how many hydrogens there are. Okay, so I think you can do this one from chemistry. In fact, I think you could have done this one before today's lesson. So I'll just give you a minute to get the answers here for this one. Yeah, please. I don't know why I wrote so many numbers down, but yeah.
What do you say is 1 kg?
1 litre is 1 kg, correct.
Liter.
Is it same as the first one?
What's that?
Sorry.
No, you can ask me a question. What's... Are you sure?
Yeah.
Okay. Maybe you need more breakfast. No? Have you got part A done? Yeah, Kim, have you got part A?
No.
Not yet. Siba? Yeah, tell me what answer you get for A when you get it there. Okay, Siba, what you get for part A?
65?
Sounds about right, yeah, yeah. Did other people get that as well? About 55 moles? Yeah, Andek?
Okay.
What did you get?
I don't want to say.
Okay, fine. Okay, what about how many molecules then? Kim, do you have that one? How many molecules?
No. 0.05?
No, it should be a big number for molecules. Did you divide? You should multiply.
1.085 times 10 to the power 28.
That sounds about right, doesn't it?
Three.
So, yeah.
3.3.
Oh. What did you get, Siba?
3.33048 times 10 to the power 25.
Yeah, because you took your 55 moles and you multiplied it by Avogadro. Yeah, grand. Okay. So what did you do wrong there, George?
Where's the other one?
What was wrong?
I had the formula down wrong. The molar mass formula.
Okay. Part C. Oh dang, what did you do?
I didn't convert.
Huh?
Convert? She didn't convert.
The kilogram.
Maybe it didn't show it.
Well, just before you work together, let's just finish the C. What's the answer for C? What's the answer for C? No calculations.
1.
Nope. Same as what?
The number of molecules.
The answer for B, yeah. Why is that? Well, because each molecule has one oxygen. So every molecule means, one molecule means one oxygen. So the answer for C is the same as B. And what about the answer for D? Times 2, because every molecule has 2 hydrogens, so you have twice as many hydrogen atoms then. Yeah. Take a minute to copy that down if you need to from somebody. 1 litre is 1 kilogram. It's like a fact. Do you need to write that down, child? Yeah.
Hmm?
You okay, child?
Yeah.
Okay, good.
Just something wrong with calculation.
George, you got it now? You sure? Calculator problem, Chow?
Yeah.
Shall we continue?
Mm-hmm.
Yeah. Seba and Company, shall we continue? Yeah. Okay. Okay, next one. Now, let's go back to Boyle's law for a moment. So you remember that, well actually, let's see if you do remember. What is Boyle's law? Ooh, there, 1 over v, yeah. So you won't be surprised to learn that there's other relationships. So that's the first one, P is proportional to 1 over v. The other one is P is proportional to T. We looked at that one. Volume is proportional to number of molecules or moles. Pressure is proportional to number of molecules. And volume is proportional to temperature. You know, again, these make sense. You know, if it gets hotter, then it gets bigger. If you have more molecules, then you have more pressure. Because remember the proof we did, we said that we think of pressure as the molecule hitting the wall. So if you have more molecules, then you have more pressure. You know. Anyway, when you look at all these relationships, it makes you think that perhaps there's one equation that all these relationships come from. So there is, obviously, and it's probably one you've seen in chemistry. So that relationship is called the ideal gas law. So this relates P, V, N, and T. What is the formula? Do you know it? Have you done it in chemistry yet? Yeah. The formula is PV equals N or T if we use moles or as a constant called the ideal gas law constant, and its value is given in a moment. If you don't use moles and if you use molecules, then the formula is PV equals NKT. That's if you use molecules where K is a constant. Okay. Now, I think both constants are on the calculator. So constant R is 27 and constant K is
35.
I don't know if that's the same one. It might be. Let me see. No, it's not. That's a different. Oh wait, no. Yeah, no, that's it. Yeah. You're right. So it's 25 and 27. Yeah, 25 and 27. So they're both on your calculator, which is handy. Not yours, I guess. I'll give you the values now, okay? Just before I do, I want you to tell me not the dimension, that's a bit, just the units. Tell me the units for R and K. I want you to tell me what the units are for R and K. So, let's have a look. I'll write it down here. PV equals N or T. Here's my question for you. I want to know what are the units here for the or. My tip is to rearrange the equation. Okay, see if you can give me the units for or. You understand what I'm looking for? Yeah. It's like what we did in lesson 1. Okay, so here you can say R is equal to PV over NT. Yeah. So what is the units for pressure? Well, that's pascals, or yeah, we'll just say pascals. Well, maybe I'll say newtons per meter cubed, because meter squared. And what's volume? Meter cubed. And what's M? Moles. And what's T? Celsius or Kelvin. Let's use Kelvin. Okay. Now they cancel. Does anyone remember what M times M is? Newton meter. What unit that is? Force by distance. Work. So what unit is that? Joule. So the unit is joules per mole per Kelvin. That's the unit for the ore. Joules per mole Kelvin. Yeah? You can do something similar for the K. And the K will be joules per molecule per Kelvin. And molecule doesn't really have a unit because it's a normal count. So this is for the ore, and this is for the K. Okay, you got that? Matt? Is okay? Yeah, I can continue. Now, we can actually see that these are the same formulas, just a different constant with different units. So, like, I'll show you what I mean. I have PV equals N or T, N or T. Now, you know that N equals number of moles by Avogadro. Number of molecules equals number of moles by Avogadro. Yeah? So if I just say N equals number of moles by Avogadro, I can put that into this formula. So I get PV equals N over Na or T. Now look, this is a constant, isn't it? And this is a constant. So I could change this into PV equals N constant over constant times T. And believe it or not, this constant is actually just the K. So if you took out your calculator and typed in constant or divided by constant Na, it will give you the same answer as constant K. So to me, it seems a little bit strange. Why do we have two formulas when they're actually the same formula? Because it's quite easy to switch between the two. You're just switching between moles and molecules. So we call the R the ideal gas law constant and the K the Boltzmann constant. But the reason we have two different constants is because we can have moles or molecules. But you can easily change between the two. So I don't know why we need to think as if there's two formulas. There's really only one formula, you know. They're really the same thing, just with different units. Why do we need two constants? I don't know. You'll have to ask your chemistry teacher. Anyways, I need to give you the values now. So the ideal gas law constant is 8.31. And the Boltzmann constant is 1.38 times 10 to the minus 23. And finally, we always use Kelvin for these formulas. These formulas don't work in Celsius. It only works in Kelvin. Okay, have you got those two values? Yeah? Continue? Yeah. So, I recommend you always use Kelvin because these formulas only work for Kelvin. Right, so I need to give you some values and then we can have a look at an example. In the exam, they'll give you the values you need for the question. So you need these values for your homework. So we have material, molar mass, and molar structure. So the first one is water, and you know that's about 18 grams a mole, and its structure is 2 hydrogen and 1 oxygen. Okay. The next one you'll need for your homework is carbon dioxide, which is about 44 grams, and it's 1 C and 2 oxygens. Hydrogen is about 2 grams, and it's H2. Oh, what do you call that in chemistry again when you have like H2 and N2? Something. Isn't there a word for when atoms come in pairs in a gas, like H2? Oh yeah, but there's a word to describe when things do that, when they go in pairs, like H2. Like I don't know, dimorphic or something. Something beginning with DI. Huh? Maybe. Anyways, the next one, helium, 1 helium, 4 grams. Oxygen, O2, about 32 grams. And lastly, nitrogen, which is N2, 28 grams. Got that? Is that you, Kim? You're hungry? Not you? Siba? Thinking about chicken shawarma? I realise it's been about a month since I had one. I think I might get one today. I'm sure there was some name for it in chemistry. You know what I mean? The 7 atoms like O2, N2, H2. There's like 7 atoms that occur in pairs in gas form. H2, N2, O2. They have a name, I'm sure of it. No? Haven't learned it? Okay. Got that? Continue? Yeah? Ah, right, one big good example to do together. So we'll do this one together. It's a big one, but it's good practice. So let's do it together. Right. A cylindrical gas tank of radius 30 centimeters and height 1 is filled with helium. So here's the picture. You've got a gas tank. It's filled with helium. What did we say the structure of helium was? Is it 1 or 2? 1. So it's just, they're all single helium atoms, okay? And the radius is 30 centimeters and the height is 1 meter. So if we wanted to, we could easily get the volume. It's pi or squared h. Can someone, oh well actually, do I have my calculator? I do. 0.3 squared times pi. 0.2827. Okay, what else do we know? The tank is in a warm room and the temperature is 26.85 Celsius. So the temperature is 26.85 Celsius. How do you change that into Kelvin? Do you remember what you do? 273.15. So it works out to be 300 Kelvin. Okay? And the tank is at this temperature too. The tank is under a pressure of 3 atmospheres. So the pressure is 3 atmospheres. Now what did we say an atmosphere was? It was 101.325? It's actually on the calculator. It's constant number 40. One oh one point 325. So it's kilopascals. So it's 101.325 pascals. Is that okay? 303975. Pascals. Right. So we know the pressure. That's good. We also know the temperature. That's good. And we also know the volume. That's good. What letter did you use for molar mass in chemistry? What letter did you use for molar mass? MR. So what is, did I say the molar mass of helium? 4.002602 grams per mole. Okay. Right, so we have a lot of info here. Let's see what we're looking for. Part A1. How many moles of helium are in the tank? Right. How can I get that one? How many moles of helium? A part 1. Do I know the mass of the tank? I don't. But if I did know the mass, I could work it out. Let's see what we can know. PV equals nRT. Okay. Do we know T? We do. Do we know R? We do. Do we know T? We do. V? We do. So we can get the N just using the formula. So let's see. N equals PV over RT. .47 moles is what I got. Okay. Right. Is that okay, guys? Yeah? Right. How could I get the number of molecules? Yeah. How can I get the number of molecules? Yeah, so it'd be number of molecules is n times Na, which is 34.47 times Avogadro's. So, what did I say? 6.02 times 10 to the power of 23, didn't I? 2.075 times 10 to 25. Times 10 to the 25. It's not really a unit. You can just write number of molecules at the end if you like. Okay? Next. How many atoms of helium are in the tank? So how many atoms of helium are in the tank? What would that be? It would actually be the same, because one molecule of helium is just one atom of helium, so it's just the same. Is that okay? So far okay? This is not too hard? Now, the next part, part B.
So, sorry.
Mm-hmm.
So the antiparliamentary is the same as number 2?
Yeah,
okay.
yeah. Part B. Some gas escapes the tank. The new pressure is 2 atmospheres. Okay? So what happens, if I look at the picture here, some gas leaks out. And the pressure, as a result, drops to 2 atmospheres. Okay, so let's write out the information again. B, in the tank. The temperature is still 300 Kelvin. The volume is still 0.2827. But the pressure is now only 2 atmospheres. So that would be 2.02650 pascals. Okay, what's my question now? How many moles of helium are in the tank? Alright, so actually if I just use this formula again, I'll get a different answer. Will it be bigger or smaller? Will it be bigger or smaller than 34? Smaller, yeah. If you were to make a rough guess, what number would you roughly say would be? Maybe half, maybe a bit more, because the pressure went from 3 to 2, so maybe, I'm guessing it'd be like maybe 20, something like this. So let's see. Right, so if I just go back on my calculator, the only number I have to change in this formula is the pressure, which is now 202,650, I think. There you go, 22.98. So about 23 moles. Okay? Now, what is the volume of the escaped helium? So this is the helium that has left the tank. What's the volume of this? So, you know, if you had your tank, and this is full of helium, the helium will escape, so it'd be like a gas of helium around outside the tank, you know. I want to know what's the volume of this gas that came out. Now, how can I do that? Well, I could use my formula, PV equals nRT, but we have to be careful because some of the values are different. PV equals nRT, and I'm looking for V. It's nRT over P. Now, what things are the same? So, is the ore the same? Yeah. Is the temperature the same? Yeah, because I said in the question the room is at 300 kelvin and the tank is at 300 kelvin. So there's no reason that when the gas leaves the tank it should be a different temperature. Okay, so that's the same. Now, what's the N? Very good, yeah, subtract them. So, what do I need? I need the difference between 34.47 and 22.98. So, 34.47 minus 22.98. So that's 11.49. Now, what about the pressure? That's interesting. What's the pressure? Why is that now? Yeah, it's just in the ground level environment, so it's just 1 atmosphere. Okay, so this will be 101,325. So if I use my calculator, times 8.31 times 300 over 101,325, 0.2827. Yeah. It's kind of funny, but yeah, I was about to say, I've done this question for like about 5 years in a row now, and only today I've noticed that it's the same answer as the tank. It just means that the volume of the gas that came out of the tank is the same as the volume of the tank. And you might say, well, how is that possible? Well, it's because the gas that comes out is under a lower pressure, so it can kind of spread out more, you know. The reason it's the same is because of the numbers I chose for the pressure, because it went from 3 atmospheres to 2 atmospheres, and then there was 1 atmosphere on the outside. The volume of the tank can't change anyways. Why can't the volume of the tank change? Well, the tank, so you can't. Right, lastly, if the tank was left open until no more helium escaped, then how many moles of helium are left in the tank? Now you might think, well, that's a silly question, because if you leave the tank open, then there should be no helium left. But that's not what happens, because it's not like all the helium will leave and then the tank is completely empty. Because if the tank is completely empty, then you have a vacuum. And what happens when you have a vacuum? The air gets sucked in. So the helium doesn't keep coming out of the tank. It only keeps coming out until what situation? The pressure. Yeah, what do you need to be happening with the pressure for the helium to stop coming out? Yeah, it needs to be 1 atmosphere. If the pressure in the tank is greater than 1 atmosphere, it will leak out. If it was less than 1 atmosphere, things will be sucked in. But when it's 1 atmosphere exactly, then there's no more escaping. Now, in real life, what will happen is some air will come in and some helium will come out. So very slowly it will turn into just air, because the helium will escape. But what I'm saying is, you know, when you turn the helium tank on and you hear it coming out, that will only continue until you have 1 atmosphere inside. Okay, but it's very difficult to actually contain helium, because it passes through materials quite easily. You know this when you were a child and you had a helium balloon. Did it stay floating forever? No, maybe 3 days, 4 days. So even though it's tied shut, the helium still escapes and exchanges place with the air, you know. So then it just loses its helium then. So, in the last picture we have, what have we got? Pressure is now 1 atmosphere. Volume is, what is it? The tank is, what did I say, 2827, was it? N is what we want. R is still 8.31, and the temperature is still 300. So I want to know the R. So PV equals nRT. So the N is PV over RT. So let's get the answer here. P V O PV over R T. 11.49. Now, because, did I ask you how many moles or how much? How many moles, yeah. If you want to, you can convert this into mass. What did we say the molar mass was of helium? What was it? Molar mass of helium? So about 4 grams. So 46 grams of helium would be left in the tank if you just left it open. Okay. Yeah, I think that was the only, maybe there's another one. No, that's it, okay. Those helium tanks, you could buy them, they're about 800 or 900 euros. You know, you see them in the shops for the balloons. Okay, now, let's see. I want you to try these for a few minutes, and then after you try them, you can decide then if you want a lecture or a tutorial. Okay, so about 5 or 10 minutes, and then we'll see what you feel you need.